Now, in the next question, we are provided with an oil drop having 12 excess electrons, and this drop is held stationary under uniform electric field of 2.55 into 10 to the power 4 Newton per Coulomb. The density of oil is given 1.26 gram per centimeter cube. We'll convert it into kg per meter cube. Hope you all know. We just multiply this with 10 to the power 3. Find the radius of the drop, and small g is 9.8. We know that the charge on electron is 1.6 into 10 to the power minus 19 Coulomb. Now here, since the oil drop is having 12 excess electrons, so the charge on drop will be Q equal to Ne, where N is 12 and small e is the charge on electron. Electric field is given to us, which is the applied field, and density of oil are represented by rho, which is 1.26 into 10 to the power 3 kg per meter cube. It is converted into SI unit. Now for balancing, mg equal to QE, and this mass is represented by 4 by 3 pi r cube rho. Hope you remember, mass is volume into density, and a drop is actually a sphere. So here I have used volume of sphere into density, which is the mass, into g equal to QE. Rearranging, we'll get small r, 3QE upon 4 pi rho g in a bracket and power 1 by 3. Here I'll take the cube root. On solving, the answer comes out to be 0.981 into 10 to the power minus 6 meter, or 9.81 into 10 to the power minus 4 millimeter. Now another very important question. 4 point charges are placed at the corners of a square of side 2 centimeter as shown. The diagram is actually given to you. Find the magnitude and direction of electric field at the center O of the square. Here, small q is 0.02 microcoulomb. Now, if you observe this diagram, we are provided with a square ABCD, and its side is small a equal to 2 centimeter. And the charges are as shown, minus 2q, plus q, minus q, and plus 2q. And we have to find electric field at point A. We have to find electric field at point O, which is the center of the square. Now here all these charges will produce field at O, and we have to find the resultant of all the fields. First of all, side is 2 centimeter, which is 2 into 10 to the power minus 2 meter. Charge is 0.02 microcoulomb. So 0.02 into 10 to the power minus 6, or 2 into 10 to the power minus 8 coulomb. If you calculate diagonal, then AC equal to BD equal to A root 2. You all know the diagonal of a square. Here we need distance AO, BO, CO and DO, and it is nothing but the half of the diagonal. So we'll represent it by small r, which is equal to A by root 2. Now here, to get field at O, we imagine a test charge. Unit positive test charge. This negative charge will attract the test charge towards itself, and we draw an arrow, and this is field due to minus 2q, and it is acting towards A. Similarly, this plus q will repel test charge towards D. So this will be the field at O due to charge plus q at B. And why it is directed towards D? Because unit positive test charge is repelled by this plus q. Similarly, this minus q will attract it. So I'll draw a shorter arrow, E suffix C. Now if you observe, the arrow EA is greater, and that of EB and EC, they are shorter. Why? Because the charges are different. Charge at B and C, they are of same magnitude. So the field EB and EC, they are represented by same length arrows. But for charge at A, the arrow is bigger. Finally, the charge plus 2q will apply electric field in repulsive mode, and the electric field will act towards B, and we call it as E suffix D. Now from the diagram it is clear that EA is opposed by EC and ED is opposed by EB. So the resultant field towards A will be EA minus EC, and I will represent it by E suffix 1. Similarly, the resultant field towards B will be ED minus EB, and I will represent this by E2. Now here I have calculated the field at O due to charge A, which is EA equal to 1 by 4 pi epsilon naught 2q upon r square. Here in place of 1 by 4 pi epsilon naught, I'll take k, just to make the question short. So EA is acting towards A, EB, which is k q upon r square, acting towards D,